All right, page 79 in your textbooks, have your homework out, and you did problems 3A and 5A last night for homework. All right. Before we get to the homework, let's go and review some things we were talking about in our last couple of lessons. As we began looking at solids, we said all solids have some degree of elasticity to them. What is elasticity, Audrey? It's not when anything. It's an ability. Start with that.
Yeah, it's an ability to bend things and they bounce back.
Well, that's a great definition for another term. What is that term she just defined, class? The ability to bend, or I think she meant to say deform things in general, and they bounce back. Resilience. Yeah. Resilience is bouncing back. So, you see a guy on in a football game just get absolutely crushed, and he pops right up off the field and keeps on going. And sometimes a guy gets hit really bad, and he just stays down. Or a soccer player, like if you touch him, he falls down and like screams. And so, anyway, that's the standing joke. Is if you expect to make money by whining, become a soccer player, but or LeBron James. And him as well. But anyway, I digress. But some things get deformed, but they bounce right back. That's actually resilience specifically, which is a part of elasticity. Kendall, how about with the more broad definition of elasticity? Because that is usually what we think of in her defense, right? We think elastic, we think resilience, but there's another aspect to it.
So like make a shape or something? Have a shape?
You want to try again, Audrey? Yeah, and rigidity is the other aspect. And what is rigidity specifically?
It's resistance against breaking.
Right, it's resistance against, not just even breaking, it's resistance against deformation at all, right? Resistance against deformation at all is rigidity, okay? But if you take both those thoughts and put them together, what was the definition I gave for elasticity?
The ability of the solid to maintain its shape.
Ability to maintain its shape. Now again, maintaining can be just not deforming, rigidity, or deforming but coming back from it, and that's resilience. We said, we talked about the plasticity of other softer solids, and what was plasticity, Kendall?
It's permanent, deformed, like permanently deformed.
It's the ability to be permanently deformed, right? The ability to have permanent deformation imposed upon it, upon some solid. Plasticity. We talked about metals and said if you heat them, they gain a degree of plasticity. You can work with metals. And what are those three metal working processes?
Forging, rolling, and drying.
Good. Forging, rolling, drawing, roll. We talked about basically what's rolling, Michael.
Rolling the metal between two heavy rollers.
And what do you produce?
Form sheets.
Sheets of metal. There we go. So sheet metal and coils of metal, even as the sheets then wrapped around itself. And a lot of metal in industrial uses is transferred that way. What about drawing? What was drawing, Kendall? Mrs. Acre taught us last year in art class. Well, yes, but in physics, what is drawing? Metalworking. What is produced through drawing? A picture. Well, I mean, she's not wrong, but wrong class. For Audrey? Wires. Wires, where the metal is forced through a single hole die to produce wires. And then the forging, back to you. Do you remember what forging is?
Is that like casting of metal?
Right, casting's the other name for it. So rolling makes sheets, drawing makes wires, forging makes whatever you want. You just have to do what with the metal?
Heat it up?
Well, yeah, so that's the true of all of them. They'll have to be heated to some extent so that way they can be workable. Michael?
Force it into a cut die.
Right, force it into a mold called a die, either two-sided, one-sided, whatever, but force it into, and then to squeeze it, pound it, smush it, I think was the word he used the other day, in the die and allow it to cool. And when it hardens, very, very strong. And again, that allows you to kind of make whatever shape you want the metal to be. Toy cars, wrenches, hammerheads, Usually hammerheads usually handles wood, but I said, it's a metal-handled hammer. It's just really heavy. Anyway, but I digress. We said that if you were to pull on the ends of a solid, you could stretch, theoretically, the solid, if you're applying a force. And the more force you apply, the more the metal, or the solid in general, rubber band, for instance, will stretch. And who noted that stretch and force are proportional to each other? Audrey? Robert Hooke. And so we came up with an equation, or say he came up with an equation, we noted the equation, called Hooke's law. What was that equation, Kendall?
F sub t equals kx.
Good, and what does the F sub t specifically stand for?
Tensile force?
Tensile force. Remember, that's that stretching force. So we did say, while tensile force stretches, it could also push inward if you went the opposite direction. What would we call inward tensile force, class? Compression. So tensile force, negative tensile force would be compression. So I guess you could argue F sub c would be negative kx. But that's, whatever. We said, though, that as you attempt to stretch a solid, or even attempt to compress a solid, there is a force that resists you. Right? There's an equal and opposite reaction force, unless, of course, you break something while you're trying to compress or stretch. What do we call the force that resists the deformation? Michael? Resist stretching or resist compressing? Restorative force. So we said that for tensile force, restorative force is negative kx. Of course, if compression has the negative, then restorative force has the positive. Because again, all a negative indicates, Michael, is
Change of direction.
Change of direction, specifically the opposite direction. And so that's how what we've looked at quite a bit. We did some math, we did some tests yesterday. Spent a little too long doing different tests with rubber bands and springs and such. And then we said this, that it's really kind of a shame that every one of our springs had to have a different constant of proportionality. It's kind of annoying, right? When they're all made of the same stuff anyway, right? Surely there would be a way to just, hey, if it's made of aluminum, it's this. If it's made of steel, it's this. If it's made of rubber, it's this. Right? Wouldn't that be nice if just every substance had this? They said, well, you have to do two things. First of all, the stretch is affected by how big the original object is. Right? Stretching something that's already very long is no great feat. But stretching something the same amount that was much shorter would be a greater feat, right? So we really want to look not so much just at stretch, but stretch relative to the length of the original object. We call this relative deformation, or anyone? Strain. Strain. So instead of just stretch, we said, well, let's look at strain more specifically, the stretch related to the original length of the object. And we said, well, also this force. Well, something that's really, really thick can handle a lot of force better. But if we accounted for the thickness, then that would allow a proportionality constant to be uniform across the board. So anything made of steel, if you're already accounting for thickness and you're already accounting for original length, then they would be proportional. What do we call the ratio or the relationship of the force per unit area causing deformation? Stress. Now again, we say force per unit area, that's pressure. Yeah, it's stress is a form of pressure that causes deformation. In fact, stress is measured in pascals, as you noted on that chart from yesterday. So we said, well, instead of just force, let's take stress, force per unit area. And instead of just stretch, let's take the stretch, or we could say the change in length, compared to the original length, and we call this strain. And these will be proportional, but instead of having a generic K, we can use it in more specific values, so that anything made of rubber has the same constant, anything made of steel, same constant. But what do we call this proportionality constant for tensile stress? Anyone?
Young's modulus.
Young's modulus, and we'll represent it with the capital letter Y in his honor. So this was our next equation then. We had Hooke's law, which is very general, very vague, and then we had more specific based on material, stress proportional to strain. But I said that nearly always, and in fact in the homework it was the case, when we solve the equation, we're going to be looking for the stretch still. How much should this object stretch based on the force that's applied, the original length, the cross-sectional area, and the Young's modulus. So I said if we want to get the delta L by itself, what will be the resulting equation or resulting fraction? Michael?
F times L sub L over A times Y.
Anyone remember the dumb way to remember this? You're smiling, you do. What is it, Kendall? Use good expression.
Flow from the progressive commercial.
Okay, so we have flow from the progressive commercial. If we saw her, what would we say?
A.
Hey! Okay, so anyway, what's up? Yeah, that's hard to put an equation for us. Let's just go with A, not even hey, because there's no H. Just A flow, but it's flow. A, we see flow first, then we say A. Okay? So anyway, however you gotta remember, if you want to be boring, remember in a boring way, that's fine too. I just remember it this way. And so this was what we were using in the homework as we look now at page 79. Read problem 3 all the way through part A, if you would, Audrey.
A copper wire 3.0 meters long with a cross-sectional area of 0.050 centimeters squared is subjected to a tension of 84 newtons. Calculate its elongation.
Good. All right. So elongation is the term for change in length. So we're finding this change in length, and we need to plug in all the numbers we know. We need to know how much tensile force is being applied. We need to know the original length of this thing. We need to know the cross-sectional area, and we need to know Young's modulus. Well, it tells us the length right off the bat, class. 3 meters. So in for the L sub O, we can put in our 3.0 meters. And it tells us the cross-sectional area, class. 0.050 centimeters squared. And it tells us the tension, or the tensile force that is applied, class.
84 newtons.
84 newtons. It doesn't tell us Young's modulus, but remember, Young's modulus depends on what is the substance in question. And what substance is in question, Audrey? Copper. So what we needed to do, and hopefully you realized this, even though we didn't have a lot of time to work on these in class, again, I said just do your best. But if you flip back to page 73, you see that table for various solid materials, and you'll see copper on there. We want to look under the Y column, and what is Young's modulus for copper? 11 E10 pascals. Does that make sense? 11 E10 pascals, and the E10 pascals is at the top of that table. So 11 E10 pascals. Now there's just one little issue here before you plug this into the calculator. What are pascals? Newtons per square meter, right? These square meters are there to cancel with, centimeters squared. So something, and again, I wanted to look at this with you yesterday. We just ran out of time, but we're looking at it now, so you may want to make some notes. I've got centimeters squared that needs to become meters squared. But centi is what, class? E-2, while meter is, so we have to move the decimal 2 places for each centimeter. But I've got 2 centimeters, right? This is centimeter. So I got to move it 2 places for the first centimeter and 2 more places for the next centimeter. Okay, we did not see that yesterday, so I have no reason to believe you would have thought of this. Okay, so it's fine if you did it, but does it make sense that that has to be the case? All right, so it becomes 0.0000, excuse me, I need the square, meters squared. And now the meters squared cancels with the meters squared, the newtons with the newtons, I'm going to be left with meters in my answer. So let's go and plug it into the calculator again. And again, my suggestion would be multiply the top, divide by this, and then also divide the 11E10. Could you multiply and put them in parentheses? Sure. I think it's quicker to say 84 times 3 divided by 0.000005 divided by 11E10. And what do we get? Scientific notation probably would be good here.
4.58 E4
I was saying that should be E-4. Good. 5.48 or 4.58. Is it 2 or 3 sig figs? 2. So we can dot. So we'll round off to 4.6. E-4. And again, our unit is going to be whatever unit the original length has. That's the same unit the change in length will have. So we'll have meters. If you wanted to think of it this way, it's 0.00046 meters. Now you could write it that way, nothing wrong with that. You could say it's 0.46 millimeters if you wanted to. I don't think you'd want to. I think you'd want to just do it this way. The reason I want to show this is that's half a millimeter. So y'all have looked at your ruler before, right? When you were a little kid and you're like, whoa, millimeters are tiny. How many thought, wow, millimeters are tiny when you were, okay, yeah, because you were interested and you were curious back then. And then you get old and boring. But yeah, the millimeter is tiny, half a millimeter. So we have this 3 meter long wire that's not quite as long as the chalkboard, but it's close. And it's subjected to a fairly strong force, and it stretches half a millimeter. Would you even notice that? No. If that force were applied, you would not say it had stretched at all, though it had just an imperceptible amount. Okay? Questions on that? All right. How many had this, but it was like E-8 or something, or E-6 or something? You did? Okay. So yeah, so for you then, it was just the decimal movement that didn't happen, which is fine, right? There was no way that I would expect you to necessarily have that. Anyone get with like an E-8 or anything like that? No?
I had 460.
460.
Yeah, but I didn't see the E10 pascals, and I didn't.
Oh, okay, so there were a couple of things going on. I gotcha, okay. So yeah, so the E10 pascals is something I pointed out at least last time. But yeah, I've not had a chance to show changing centimeters squared into meters squared or anything like that. So does it make sense at least now? Okay, and again, I knew there was a good chance we weren't going to get them, but at least give you a chance to think through the process. Makes it a little easier to move on today. Let's go on to number 5A. 5A, and read that for us if you would. Michael.
A brass wire 2.5 meters long has a radius of 1 millimeter and hangs from the ceiling. If an object weighing 12.2 newtons is suspended from the lower end, what will be the elongation? All
right, and so we had an aluminum wire 6 meters long. Let's see, that's about a 2-story building height. Okay, so we have this long wire hanging down 2 stories. What?
We're on 5.
Number 5. Right, okay, brass wire, yeah. 2.5 meters. That's about the height of the room. Okay, so about the height of the room ish, plus or minus ish, and a radius of 1 millimeter. Radius of 1 millimeter. Is that the same thing as area? But I can use it to find area, can't I? So let's go and set up our problem here. We've got our change in length that's going to equal flow over A. The force is not much. It's about 3 pounds. Class? 12.2 newtons. I mean, all of you, I gave you those weights, those masses yesterday, right, to hold. That's about 3 pounds. Okay, so that's not, I mean, it's not that much, especially compared to the previous problem. And the original length of the wire, it said, was 2.5 meters. All right. Let's go ahead and get the Young's modulus. How do I figure out which of Young's moduluses is to use? Moduli. To use.
Go to the chart.
And look up
Brass.
brass. So you're looking at the material it's made out of. And what do we have for brasses is Young's modulus?
9.1 E10 pascals.
The 9.1 E10 pascals. All right, finally we come to the area. But how do we calculate area? It wasn't given to us like it was in 3A, right? All it did was give us a radius. Well, that means the wire's cross-section is a circle, correct? And so to find this cross-sectional area, I need the formula for the area of a circle, which is pi r squared. A equals pi r squared. So we've got pi, of course, and the radius is 1.0 millimeters, and that has to be squared. Well, wait a second. Can I work with millimeters? But you might not have thought of that last night, right? Because you weren't thinking about the newtons per meter and the meter squared in pascals. So I do want to change this. Before I go squaring it, let's change the millimeter into meters. Move the decimal 3 places. And we haven't squared it yet, so it really is only 3 places. When I move it 1, 2, 3, that's going to factor in 2 extra zeros, right? 0.001 meters, and we'll square that. So at your seats, go ahead and square the 0.001 and multiply by pi. You'll get something like 0.000031415, blah, blah, blah. Put that in the memory of the calculator. And we'll get to it when we get to it. Now it's easy. That was the hard part. Now it's just the 12.2 times the 2.5, divide out the recall, and to divide out the 9.1 E10 pascals. Once again, put it in scientific notation if it was not already. And what do we get for the change in length?
1.1 E-4.
we have 1.06 blah 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 e negative 4 rounds to, it is still 2, yes, 2 sig figs still, 1.1 e negative 4. Oh, careful. The pascals are the newtons per meter squared, so the meter squared and meter squared cancel newtons and newtons, so just the meters. And again, if you wanted to, you could think of this as 0.001 meters or 0.11 millimeters. About a tenth of a millimeter is all it stretches. Well, to get a visual here, you have a mechanical pencil there. That's 0.7 lead. How many mechanical pencils? 0.7 lead's pretty common. I'm a 0.5 guy personally, except on standardized tests. 0.7 is good. Have you seen the 1 millimeter pencils? The 1 millimeter pencils, really thick lead. 0.9 was what they came up with next, and then just went to the 1 millimeter pencils. Well, that's the diameter of the lead. So we're talking twice as thick as that now, right? So twice as thick as the thick pencil, and that's pretty thick. That's a decent size thickness of brass wire rather. Hanging from the ceiling, you tug on it, put those 3-pound weights on it. It'll stretch it out a tenth of a millimeter. You would never even notice. Right? Questions? All right, let's look back now at page 74. Look back now at page 74. Let's look at a compression problem. And read this for us if you would, Kendall.
25 centimeter long bond with a cross-sectional area of 3.20 centimeters squared supports a load of 2,200 newtons. Calculate the compression of the bond and the length of the bond after it is torqued.
All right. So this would be, for instance, if you are carrying something heavy, right? Or maybe carrying a small child on your shoulders, your body compresses. Now, admittedly, most of the compression is going to affect the joints more than the bone itself, okay? But let's just say the bone itself somehow receives this compression. It's a 25 centimeter long bone, so that's a little smaller than a foot long in our vernacular, so maybe Kendall's femur bone. Okay. I'm picking on you. Maybe that's what happened. Your bones got compressed too much, and I'm just picking on you. All right, anyway. So we want to find the compression of the bone. So we're finding a change in length, right? Change in length is compression, right? Now, it's a negative change in length, right? We'll expect to get a negative answer, but change in length still negative. We don't need to highlight anything right now. We're not even there yet, Michael. Change in length can be elongation when force is positive. Change in length will be negative. It'll be compression when the force is negative. So as we go to set this up, and when we plug in the force, what was the compressive force again, Kendall?
2,200 newtons.
But we're going to make it negative 2,200 newtons. If you need to, put this in your notes, make sure you mark it down. Compression force is always negative. Compression force is always negative. And because it is negative and everything else is positive, that'll produce the negative change in length, which means shrinking. Positive change in length, growing. Negative change in length, shrinking. All right? The original length of the bone, Kendall?
25 centimeters.
Now, normally, class, I would say we have to change to meters, right? But remember I said whatever unit you have here is the unit that will end up here? I'm lazy. I'm going to leave it 25 centimeters. In the area, that has to be meters squared because of the pascals. The original length can be whatever unit you want. Now, if you say, I would get confused and forget when to do what, then by all means, go with 0.25 meters. It's not wrong to change to meters. If you're just like, I just want to always know to change to meters, that's fine. But I do want to point out you could get away with leaving the 25 centimeters here. Let's jump to Young's modulus before we look at the cross-sectional area. For bone, what is Young's modulus for bone?
1.85 pascals.
1.8
E10 pascals.
E10 pascals. All right, and then we need the cross-sectional area to be in square meters. And we were supposed to do this problem yesterday in class. This was going to be the next thing we did when we ran out of time. So you would have already seen this. What did they give you for that cross-sectional area? And this was when I was going to teach you, before you did the homework, that you got to move the decimal, how many places? 4 total. Twice for the first centimeter, twice for the next centimeter. So 1, 2, 3, 4 fills in 3 zeros to get meters squared. Does that make sense? By the way, what if they gave us millimeters squared. How many places would I have to move the decimal? 6. 3 for the first millimeter, 3 for the second. What if we were doing volume? I know this is a long time ago. Remember we talked about density, mass divided by volume? And what if the volume had been centimeters cubed and we needed it to be meters cubed? How many places would we move the decimal? 6. 2 for the first centimeter, 2 for the second centimeter, 2 for the third centimeter. Does that make sense on the complex unit? Not something I don't think you'd seen that last year in chemistry. Had you? No. Okay, so that is new. I was pretty sure it was. All right, so there we go. So on your calculator, go and plug it into negative 2,200. I'm going to just go times 25. Divide by the 0.00032 and divide by 1.810. And what do we get for the compression of the bone?
0.0095.
Yeah, centimeters. Now that if you were to round to only 1 sig fig, that'd be 0.01, right? That's 1/100th of a centimeter. That's 1/10 of a millimeter. The bone is barely compressed at all. Okay, even if there weren't the joint to absorb it around it, right? Just the bone being loaded. So 0.009, surely it was 2 sig figs, right? 5 centimeters? Or you could do negative 9.5 e negative 3 centimeters. If you changed to meters, it would have been an e negative 5 meters. And I'm going to leave it centimeters. Yeah, I'm definitely leaving it centimeters because that's not the final answer. Part A says to find the compression of the bone. But look at part B. Kendall, read it again.
The length of the bone after it is loaded.
Find the length of the bone with this compressive force on it. So, for instance, maybe there's these two, I'm picturing, you know, in the Death Star when they're all down in the trash chute and the compression starts coming in and they put a pipe in between, right? But imagine, or better yet, the monster in episode 6, right, where he's fighting the monster. He sticks the bone in his mouth to hold his mouth open. Anyway, okay, being crushed slowly. Okay, you're not a Star Wars person, so don't worry about it. They know what I'm talking about. What?
Are you talking about movies like?
Movies, Star Wars movies.
Okay.
Yeah.
You said episode. I'm like, what?
Yeah, the Star Wars are in episodes. There's episodes 1 through 9. 7 through 9, don't waste your time. That rhymes. BB-8's cute, but other than that, I mean, it really is. It's such a lame storyline. And they destroy all the good characters. Like all here. Yeah, there's a side of me wishes they just never come out with them at all, or done a much better job. I mean, that's really what I wish, right? Because I like more. I thought more Star Wars would be good for the world, right? We need more Star Wars. But anyway, I digress. Grace Christian School does not necessarily endorse movies, actors, or anything else produced. But anyway, but it says find the length of the bone. Well, the bone was 25 centimeters, right? How do I find the length of anything after something's taken place? Well, you would add the change, correct? So if Kendall grew 2 inches, we don't know how tall is Kendall now. Take her height before, add 2 inches, that's her height now, right? She's not that short, come on, man. But if Kendall shrunk, maybe she's 70 years old now, and apparently scientifically they say your body shrinks as you get older. I think that's probably true. Well, if she shrunk, then we would add her negative change to that, right? So we're going to add the negative 0.0095 you have on the calculator, add that to the 25 centimeters it was originally, and now what's the length of the bone?
24.99045.
Okay, good enough. Okay, so 24.9 and blah, blah, blah. How many sig figs are we allowed? Still just 2. So we cut off at 2 sig figs, how long is the bone? 25 centimeters. When you round to 2 sig figs, no compression really happened. If you went to 4 sig figs, barely any compression happened. So, not much. Questions on this, though? All right. Look now, if you would, page 79 again. Let's go back to page 79. I want you to do number 6A. Page 79, you do 6A. Now that we've done a couple of these together, I want you to try number 6, letter A. All right, go ahead and read 6A for us, if you would, Audrey.
An aluminum wire 6.0 meters long with a diameter of 1.00 millimeters hangs from the ceiling. If a mass weighing 140 newtons hangs from the lower end, find a elongation.
All right, what equation do we need to find the elongation of an object subjected to tensile stress? Michael?
Delta L equals force times L sub O divided by A times Y.
All right, and then in for the force, what do we plug in, Kendall?
140 newtons.
All right, so what is that, about 30-ish, a little bit more than 30 pounds? That's a pretty good. That's that's like a 2-year-old hanging from it. Okay, how long is the original length here, Audrey?
6 meters.
Okay, so this is that 2-story long wire. Maybe this is like hanging from a museum or something. There's like a pendulum or something hanging and a little kid jumps on it. Of course, then what's the weight of the pendulum? I don't know. Anyway, the cross-sectional area, did they give us that number, Kendall?
They
They gave a diameter. So if the diameter is 1 millimeter, then the radius would be 0.5 millimeters, but I don't want millimeters, so I need to then change that to meters. How many meters is the radius?
0.005.
Well, how many places do I have to move the decimal?
3.
So since the decimal's already in front of the 5, that's actually giving us 0.0005 meters. That's our radius. What do I need to do with the radius, Michael?
Square it and multiply by pi.
Square it and multiply by pi. So we square the 0.0005 squared times pi. I'm just going to put that in memory 1. Stow 1. All right, and then Young's modulus. This is an aluminum wire, you said. What is the Young's modulus for aluminum? 7.0 E10? Pascals. And so from there, you just plug in the numbers, right? You just take your 140 times 6 divided by recall 1 divided by 7, E10. And a little bit more stretch this time, right? Because we've got a little bit more force this time, and it's a little longer to begin with. So it allows for more stretching. There's more molecules to slightly separate, right? That's really what it is. Remember, it's the cohesive bonds, and the molecules tightly packed. The molecules slightly separate from each other. Not enough to break, but slightly enough to cause the stretching. That's what's happening. And, or thinning out, I guess, technically, as they stretch. But what do we get for our answer here? Audrey?
1.527
Good. Or 0.0152, blah, blah, blah. If you didn't want the scientific notation with an E negative 2, round it off, 0.015 or 1.5 E negative 2 meters. So that's actually 1.5 centimeters. Now, when it's 2 stories long, would you notice a 1.5 centimeters? I'm not sure that you would. It's still rather small, but I mean, it's the most we've had so far of any stretching material. Questions on this? Do we get the 0.015 or 1.5 E negative 2 meters? Does it make sense now? All right, take a look at number 7 and read that one for us, if you would. Kendall.
A platform is supported by 4 solid steel bars, each 54 centimeters long, and with a cross-sectional area of 3.6 centimeters squared. By how much is each compressed if an 8,000 Newton elephant stands on the platform? Assume each leg supports 1/4 of the weight.
All right, so it's like a circus platform or something. They'll lead the elephant up onto the platform for some reason. I don't feel how it could be that strong of a platform, or it has to be a pretty small platform to only have 4 steel bars. Surely you'd reinforce the middle, but they don't. Also, it doesn't tell us the weight of the platform. But we're not going to worry about any of that, okay? We're just going with the elephant. The elephant, it is an infinitely massless platform, yet somehow supports the elephant, and there's no center support, yet somehow it supports the elephant. I don't know. Okay, we're just going to go with 1/4 of the elephant's weight compresses each of those bars. Does that make sense? Or each of those vertical bars, I would say. So how much force pushes on each one of these bars, class?
18,000.
Well, that's the total elephant, but there's 4 bars, so 1/4 of the elephant for each one.
4,500.
Yeah, 4,500 newtons is being supported by each of these bars, or rather, is compressing each of these bars. Now, if it's compression, what do I have to remember? Put in negative. It's negative 4,500 newtons. Original length of each of the bars, it says, is?
34 centimeters.
Do I have to change that to meters? I don't have to, not for the original length. Can I? Sure, I don't have to. There. Cross-sectional area, it tells us.
3.65 meters squared.
Do I have to change that to meters squared? Yes, area does because of the pascals and Young's modulus. So what does that become when we change it to meters squared, Kendall?
0.00036.
One too many. Remember, the decimal's between the 3 and the 6, so 1 is here, and then 2, 3, 4 gives us just 3 more zeros. So 0.00036 meters squared is our area. And then these bars, it says, are made of steel, or support posts, I guess you might call them, made of steel. Young's modulus for steel.
20 point.
E10 pascals. Newtons and meters squared cancel with the pascals. And let's go and see how much compression happens to each of these posts.
Negative 3.4 E, negative 5.
I got a negative 3. Anyone else get a negative 3? Okay. Oh, did you change this to meters?
I did.
Okay, that's why. So yours is not wrong, okay? So both answers are correct. Either negative 3.4 E negative 5 meters or negative 3.4 E negative 3 centimeters. Either answer is fine. But barely any compression at all. Barely any compression at all. Right? So again, when we say definite shape, an elephant barely did anything. Okay, it's pretty much definite shape. Imperceptible changes to shape, perhaps, as far as stretching and compressing is at least concerned. We'll look at other types of deformation in your reading tonight. Let's talk a little bit about how this stretch occurs. And I referenced some things yesterday because you remember when we stretched the springs and we ran some calculations, everything did what we expected to pretty much with the springs, remember? Well, the rubber bands were weird. We stretched out the rubber bands, we got our readings, we stretched out the rubber bands again, and it didn't do what we thought it would do, did it? The proportionality didn't seem to be there. Well, there is a proportional relationship per Hooke's law, but it exists for small deformations. There is a point at which, if you continue to apply more force or more stress, you'll get faster deformation, more rapid deformation, the proportionality breaks down. We call that point the proportional limit, and I referenced it yesterday, but go ahead and get it in your notes now. The proportional limit refers to the point at which Hooke's law is no longer valid. Okay? Restorative force will no longer be proportional to elongation. It elongates faster than Hooke's law would expect. Okay, the proportional limit is the point at which Hooke's law no longer applies. Restorative force is no longer proportional to elongation, Stress is no longer at that point proportional to strain. The object begins to elongate more rapidly because the greater amount of force is present. I think with one of the rubber bands, we put a larger mass the first time, a smaller mass the second time, and the smaller mass didn't stretch it as much as we thought it should. The larger mass had apparently stretched it past that proportional limit. In the other instance with the rubber band, we put more weight the second time, and we did our calculation and stretched it more than we would have expected. Well, again, that greater weight caused more stretch than was proportional. Does that make sense? So the proportional limit, there is that point for all materials, but within small deformations, and the book makes that clear, within small deformations, Hooke's law is valid. You could continue stretching past the proportional limit to a point called the elastic limit. The elastic limit. Now this is what I referenced with the shorts that my wife put on when she was pregnant. She stretched them to the point of no return. No longer would the shorts stretch back to their original shape. No longer does the rubber band bounce back. Not broken, but it's overstretched. I think a great example of this would be socks. Y'all know socks have the elastic all throughout, around, up the sock, around the top, all over the place. I don't know how much it affects you ladies, but I'm sure, Michael, you know what I'm talking about. The top of the sock, take it out of the dryer, and it's your dad's socks, perhaps, okay? Why? Because men tend to have large calf muscles. And the sock was not designed, it's designed to fit tight to the calf muscle, but over time, it just stretches it to the point of no return. Okay? Now, in that case, that's kind of an overtime wear and tear kind of thing. It didn't happen the first time you put on the sock, probably. Okay? Unless, of course, you were snapping elastic fibers as you pulled them up. My son loves to tug his socks as high as he can get them. And so his socks are very long, okay? Elastic limit specifically is the maximum stress. Now, that's force per unit area, remember. So we're thinking of how much force is applied, essentially. The maximum stress that can be applied without permanent deformation. This is actually partly how we define resilience. Remember, resilience is defined as a material with a high elastic limit. It can endure a great deal of stress before permanently deforming. In other words, it bounces back easily. Okay? The elastic limit is the maximum stress an object can sustain without being permanently deformed. You could apply more force and you will continue to stretch, but it ain't going back. It ain't bouncing back. Its resilience has reached an end. Okay, it's the maximum stress that an object can sustain without breaking. But you could still apply more force and it would continue to stretch, and continue to stretch rapidly, I might add, because we've already passed the proportional limit. Then we come to the ultimate tensile strength. The ultimate tensile strength. That refers to the maximum stress the object can sustain without breaking. If you put any more force on that object, it will break. It cannot handle any more force. It cannot handle any more force. You put more force, it breaks. That's the ultimate tensile strength. The maximum stress an object can sustain without breaking. It just can't handle it anymore. Too much. Now, oddly enough, the object doesn't necessarily break at the ultimate tensile strength, though it usually will break shortly thereafter, because so long as you don't add more force, the force is not breaking it. You're adding more force, and it continues stretching just a little bit more, perhaps, because again, it's stretching more rapidly than Hooke's law would allow, but then at some point, the actual stretch is too great. It has been stretched too thinly, so to speak, and it finally breaks at what we conveniently call the breaking point. The breaking point. Now that's the maximum strain the object can endure. The breaking point is the maximum strain the object can endure. The maximum strain the object can endure. In all fairness, the ultimate tensile strength and the breaking point are usually really close to each other. Usually you wouldn't be able to tell a perceptible difference between them, okay, unless you were dealing with very carefully regulated amounts of force, which is challenging to do in a lab setting. But theoretically, okay, that's where we're at. I say theoretically as if it hasn't been observed. It's been observed. We would probably be able to do it with the instruments we have, okay? But so you start to stretch something. And you stretch and you stretch and you stretch and you stretch. Maybe it's the rubber band. I've got one in here. Where's my rubber band? Nope, it's in the other room. That's okay. So anyway, we take rubber band and we start to stretch. And at some point, even though we're not applying as much, it starts to stretch more than we would think it would based on the force. That means we've passed it stretches more than it should based on the force we're applying. Proportional limit. If we keep stretching and stretching and stretching, just keep putting a little more force, a little more force. It's pretty much stretched out. You know what I'm talking about? When you pull the rubber band all the way back, and just keep carefully, just a little bit more, a little bit more. Try not to break it. You could get to a point where the rubber band is not going to go all the way back to its original shape. It may even come in somewhat, but it's not going to recover its original shape. That means we've applied so much force or so much stress that we've passed if it won't bounce back. The elastic limit. It won't bounce back. That's the elastic limit. We could keep applying a little bit more force, but at some point, if we apply more force, it breaks. What's that point at which if we apply more force or more stress, it breaks? Ultimate tensile strength. But if right as we get to that, we somehow know, I can't put any more force on this thing. Maybe we even relax the force and just kind of pull it. It might stretch just the tiniest bit more, even though there wasn't additional force. But then it has stretched out too much. It can't handle any more elongation. It's reached its point of maximum strain. What do we call that? Breaking point. Does that make sense? Now, there are some things, for instance, a rubber band that was dropped on the driveway, and it got rained on, and then it baked in the sun, and you pick it up, and it doesn't stretch, it just breaks, okay? Some substances are like that. Elderly people's bones, they can't handle the compression that we talked about in that one problem, right? They break, and that's one of the hazards, one of the things you have to be careful with elderly people, of course, making sure they don't fall, because their bones break so easily. Things that break rather than deforming are referred to as being brittle. Brittle. Mom's china. Well, I thought I could bend that plate. No, it breaks, okay? Brittle objects don't deform, they just break. So objects that break suddenly without deforming first are called brittle objects. Brittle objects. And unfortunately, I think that's about all the time we're going to have, which is a shame. So we're going to do some math with the ultimate tensile strength and the breaking point, the elastic limit, and the proportional. We're going to look at some of those things in our next lesson. For homework this evening, I need you to read pages 75 to 78. Pages 75 to 78. Yes. On page 79. Page 79, do questions 9 through 12. Page 79, questions 9 through 12, and problems 4A and 8. Problems 4A and 8. And we'll take a look at all of that in our next lesson. All right, when the bell rings, you'll be dismissed. Have a wonderful rest of your day.